So in that previous question, we have this diagram here, but the most important, we can solve this in many ways, but the most important thing to note here is that these two lines here are symmetrical by this diagonal, which means that the point in which the two lines meet is going to be the center of this rectangle right here. And therefore, we can split it up like this and also like this. We know that this length is 4 and this length is 1. And this length is 7 and this length is 1, which means that this side in total is going to be 8. And because this is the center, this length will be 4, which is half of it. So the area of this triangle will be this 1 times height divided by 2. We have 2 of them, so we're going to multiply 2 anyways. Which means that if we add up this triangle here and this triangle here, it's going to be 1 times 4 divided by 2 times 4. The other triangle here, we apply the same method. So this is 4. And this is going to be 5 over 2 because this length is 5 and this is the center, which means this length is half of this length. So if we multiply base times height, and then multiply 2 because we have 2 here, 1 here and 1 here. If we sum them up, it's just basically going to be 13 over 2. We first draw, for the in-center, we first draw the height. We clear things up a little bit on this triangle. So we first draw the height, which is going to be h, and we use Pythagoras Theorem on this triangle here, which gives us this length is root 64 minus h squared. And then we also get an expression for this length by using the Pythagoras theorem in this triangle, in this right triangle. And then because we have one variable and one equation, we can solve this length for h. And this is one of the solutions that you can use to get the area. But the other solution that I used is to use Heron's formula, which is an equation which is a formula that you use to get the area when you know the 3 sides of a triangle. So to recap, last time one of the methods that I talked about over at that board was if small h is the perimeter of the triangle divided by 2, then the area equals s times s minus a times s minus b times s minus c. We can just directly use this in this case because we know 8, 7, 10, which is each of the length of the triangles, each of the length of the sides of the triangle. So plugging these into this equation here would give us the area. And then if we know the area as you correctly pointed out, we can use this equation, which is the area that we use to get the, which is the formula that we use to get the area of the triangle when we know the in-center radius and the length of each of the sides. So we know this by plugging in the values, and we know this because we know each of the sides. And then by solving it for r, we can easily get the length of the in-center's radius. The calculation, I should have actually used 9, not 10. So the calculations are very, very dirty, and apologies for that. So I won't go into the calculations, but this is basically how you would approach to find the length of the in-center and the x-center. And then in the case of the x-center, we can also we can put the coordinates for each of the points, and then we can use the Shoelace theorem or the Shoelace method. But another way is, we know the area by this Heron's formula here. And then last time, we talked about how if the x-center's radius is big R, the area would equal, does anyone remember this formula?
4r.
Yeah, the denominator was 4r. So this would also be equal to the area of ABC, and because we know by Heron's formula what the area is, this would also equal to this. And then if you just plug the values into A, B, and C, we can solve it for R again. Again, this is supposed to be a very easy calculation, but yeah, the 10 messed it up. Are there any questions before we move on to the next question?
So we're ready for the next one?
And the next one is quite hard because I made the questions to like become more difficult as we go to the next questions. So the next one might be quite difficult. So to give you a hint, what you might want to use is to put B as the origin and put this triangle on a coordinate plane, and then getting the coordinate of I and O, and then using the Shoelace Theorem here. So if you don't remember what the Shoelace Theorem was, it was getting the area of a triangle with each of the coordinates. So let's say that A is x1, y1, B is x2, y2, C is x3, y2, y3, then the area of ABC equals 1/2 times what we then do is that we multiply these together. And we also do it the opposite way as well. And this looks like a shoelace, so that's why the name is a Shoelace Theorem. And the proof for this, you can get it by using vectors. I'm sure that the proof is also on Google Classroom as well. That is correct. So first, what we want to do is that we place this on a coordinate plane, and then the really important trick in this question, as you can see in the diagram, was that point O is actually the circumcenter, and on right triangle, the circumcenter has to be on the hypotenuse, on the actually the midpoint of the hypotenuse. So by that, we can just easily get the coordinate of this one here. And then when we get O, we can use this formula here, which is the area equals the half of the perimeter times the in-center radius, and then we use it to get the in-center, this just gives us 1. But because B is the origin, if we have a circle on there, if we have a circle that's tangent to the x and y, the x and y axis, the center of the circle can be just expressed as a comma a, because this length equals to this length, because they're both the radius. And then this means that if the radius is 1, this in-center is just going to be located on 1, 1. We know that this point here is 0, 0, and this point here is 2, 5/2. So because we know the coordinate of each of the points, we can just easily use the Shoelace Theorem. So in that sense, what we can kind of like learn from this, the takeaway of all these 3 questions is that normally if we have 3 lengths, the 3 lengths of each of the sides of a triangle, what we want to use is normally the Harris formula. And if we have the coordinate of each of the points on a triangle, what we then want to use is probably the Shoelace formula, because they are probably the easiest way to just get the area of the triangle right away. We could still apply Harris formula by using Pythagoras to get each of the lengths of the sides, but it would be a very tedious and lengthy process. So we will probably want to use and apply the Shoelace theorem in this case here.
Shoelace theorem. Shoelace. SHVLAC.
So today's lecture material, this can be actually quite difficult, but since we are trying to explore math, let's also explore difficult things. So today's content is going to be inequalities and how they can be applied into geometry. So does anyone know does anyone know the arithmetic mean, geometry mean inequality? Please raise your hands up if you know it, or at least if you're familiar with the concept, please let's see a show of hands. Only one person? Okay, one more. Okay, I see a few hands. So what that inequality basically is, so today we're going to cover only two inequalities. First one is the arithmetic mean versus geometry mean. Second one is the Cauchy-Schwarz inequality. I'll just write it as AM, GM. So AM stands for arithmetic mean, and GM stands for geometry mean. And so this is basically the arithmetic mean is if we have numbers x1 to xn, it's just the average that we're being familiar with. So it's just adding up all of the numbers and then dividing it by the number of data that we have. So it would just be x1 plus x2 all the way up to xn, and then just dividing it by n. On the other hand, the geometric mean would instead multiply all of them together and get the nth root of it. So this one here is called the arithmetic mean, in short AM, and this one is the geometry mean. The reason why we want this as well is because in some cases, with some data sets, it's really difficult to use this one to get the accurate average. So say, for example, if we have a data set that increases like 1, 30, 900, 2700 or something like this, then in this case, 27,000. In this case, they exponentially increase. So if we get the arithmetic mean, it's probably not going to be an accurate representation of this data, but rather this one would be probably a better way to represent this. So in different data sets, we want to use different means. And if there are people who are already familiar with this, you can also research the harmonic mean and the root mean squared, which is basically like an extension of the arithmetic mean and the geometry mean. With every data, if n is a number that's equal or greater than 2, so if we have 2 or more data, the arithmetic mean always is greater than the geometry mean. For those who are familiar with this geometry mean is always greater than the harmonic mean, and the root mean squared is always greater than this. Since we're kind of like running out of time, you can research this at home in your free time, and these will also have like really interesting properties. But besides that, we also have Cauchy-Schwarz inequality, which in short I'll just call CSI, Cauchy-Schwarz inequality. In this inequality here, let's say that we have data A1 to AN. These are all real numbers. On the other hand, let's say that we have B1, B2, all the way up to Bn. So in here, we have n data here, and here we also have n number of data. And when I say data, it just basically means numbers. We have n numbers in here, and we also have n numbers in here. Then, for this set of numbers here, let's square each of them and add all of them up together. And then we also do the same thing for B1 up to Bn, and then we multiply them. Then this equation, this expression here, is always greater than us multiplying A1 with B1 plus A2 with B2 all the way up to A and Bn squared. So So it's basically the sum of the squares multiplied is always greater than the sum of the multiplied squared. And we do not have enough time, so I think we will be able to prove either one of these, or we might just move into questions using these. Which one would you prefer? Do you want to prove either one of the two or solve questions? Who wants to prove? Who wants problems? Guys, come on, let's all vote. Who wants the proof? Who wants the solution? Who wants the problem? Sorry, not the solutions. We have an overwhelming majority that wants the proof. Then which one do you want to prove? This one is harder to prove than the Cauchy-Schwarz inequality. Who wants the proof for the Cauchy-Schwarz inequality? This one is the easier one. A show of hands, please. Who wants to prove the harder one? Okay. We have a very strange group here. Okay, so let's prove this. To prove this claim right here, we need to use a special tool that's called mathematical induction. Is everyone familiar with the term mathematical induction? Who knows what induction is? Okay, so for people who are not sure about what induction is, when we're proving a claim like this, so let's say that we want to prove fx equals fn equals gn. So here, this expression here is dependent upon n. So let's say that we want to prove fn equals gn. In mathematical induction, what we first do is that we do something called the base of the proof. So in here, we just first prove that f1 equals g1, f2 equals g2, and we prove two of these trivial ones. These are really, really easy ones, right? We can just plug the numbers in, and they'll give us a very easy and trivial proof. And then the second thing that we do is that we assume that this is true for n equals a certain k. K is any number. So we assume that this is true for n equals k, and then we prove that that expression holds true when n equals k plus 1. So from this, we know that fk equals gk. So using this fact, we try to prove fk plus 1 equals gk plus 1. And then this is the end of the proof. So you basically assume that it's true for a certain case, and then you apply that fact in order to prove that it's going to hold true for the next one. And the reason why this makes sense is because what we basically did is that we said that this expression makes sense for f1 equals g1. And then we said that if n equals k and it holds true, it would also hold true for the next one. So because we know that this expression holds true when n equals 1, because of this statement here, it would also hold true when n equals 2. And then because it holds true at n equals 2, it would also be the same for n equals 3, and so on, up to n equals infinity. So that's why mathematical induction is logically sound. So we're going to use that in order to prove this claim right here. So first, base. Let's consider when n equals 1. When n equals 1, we have x1 is greater or equal than x1, and therefore this holds true. This is really trivial. When n equals 2, we have x1 plus x2 over 2 is greater or equal to this. this is the claim that we have to prove when n equals 2. And to prove this, we might just want to move this 2 over to here, because we can multiply 2 on both sides, and then we just square both sides. If you subtract this from this side here, this is what you have to prove then. But this is true, because this expression here is just x1 minus x2 squared. And the square of a number is always greater or equal to 0. So at n equals 2, we will show that this is true. But are there any questions or anything unclear until this stage? No? Okay. So we just proved the base case, and then we now move on to assuming that it holds true at n equals k. Which means that if we try to express that mathematically, so from this fact, we're going to show two things. The first one that we're going to show is that if this holds true at n equals k, then so if n equals k and then true, this means n equals 2k is also true. This is the first thing that we are going to prove. The second one that we're going to prove is that if n equals k and it is true, then n equals k plus 1 and it's still true. Do you get what we're trying to do here? We are first trying to prove that this was true at n equals k and n equals 2k, which means that this would be true for every single one of the even numbers. And then if we prove that this one is also true, it would just basically hold true for odd numbers as well, because if we add 1 to an odd number, to an even number, then it would be an odd number. And all numbers are either even or odd, which means that if we prove these two claims, this inequality would be true for any number. So the first case is, let's try to prove that this is true when n equals 2k. So when n equals 2k, let's split. We first have x1 all the way up to x2k, and then split it up into x1 all the way up to xn, and x1 all the way up to not x1, because we're splitting it. Xn plus 1 all the way up to x2n. So in here we have n numbers, and we also have n numbers here. Which means that, oh, I am very sorry, k numbers here and k numbers here. So we basically split this 2k numbers into half of it, where in one side there are k numbers and the other side there are the other k numbers. Because we assume that the AMGM inequality is true when n equals k, we know that AMGM holds true in this set and also in this set. So firstly, for x1, should I actually move over to that board? Will it be easier for you to see?
And you wouldn't have to erase as often.
Yeah. Okay, I'll just go over to that board. basically here, let's say that the arithmetic mean of these numbers is m1. So m1 would equal x1 all the way up to xk divided by k. And because we know that the arithmetic mean, geometry mean holds true at n equals k, this would be greater or equal than the geometry mean of these numbers here, which means that this is greater or equal than x1 multiplied all the way up to xk. We do the same thing for this one, and let's call this g1. We do the same thing for this one. And then let's call this g2 in this case. Then let's consider the arithmetic mean of the 2k numbers, which is all of these combined together. That will be x1 added all the way up to 2k divided by, what would it be divided by? Yeah, it will be divided by 2k, because this is the arithmetic mean of all of these numbers here. And if we look at this, this is actually 1 over 2 multiplied to this. And here, we can just split this into half again, because then we would have split this up into like this. But note here that this expression here, x1 added all the way up to xk divided by k, is equal to the arithmetic mean of x1 to xk. So this, the first one becomes m1, the next one becomes m2, because we know that this expression here just equals to m2. But do you remember that we proved that the AMGM inequality holds true at n equals 2? Which means that if we have two numbers, we can use the AMGM inequality because that was one of our base case. Our base case was n equals 1 and n equals 2. Because we know that this holds true at n equals 2, and we have two numbers here, we can again apply the AMGM inequality to these two numbers. So by applying this one, we can change this expression to this because both are greater than these two. So adding them together will still be greater than adding these two together. So we know that this one is always greater than this. And then if we use AMGM inequality to these two numbers, because as I just said, our base case was n equals 2, this would be just equal to this, because this equals the arithmetic mean of the 2, and this is the geometry mean of the 2. And then if you look at this expression here, if you multiply these two together and then get the roots of it, that will just equal the geometry mean of all of those 2k numbers. So here we have just proved that in the first case, where x1, where we have 2k numbers, the AMGM inequality holds true. And again, we do the same thing for k plus 1 numbers. We're actually running out of time. So with k plus 1 numbers, we do the same thing. It's just that we add one more variable. It's just that we add one more number and use that instead of 2k. And then by applying the same logic, we can prove it for k plus 1. And therefore, we prove the arithmetic mean, geometry mean inequality for all numbers. Because we just proved that it holds true for odd numbers and for even numbers and odd numbers as well. So that's basically the end of the proof. And it was very difficult. It was a very tedious way to get here. But in essence, I think that the most important takeaway of all of this is just mathematical induction about how you can prove on seemingly really difficult things by just setting a base case and then proving a rule and then applying that to the base case to get